The last 3 lectures is to talk about the holonomy groups G2 and spin 7. So let's have a new section, section 5, on these. Okay, so these are called the exceptional holonomy groups. They are G2 in 7 dimensions and spin 7 in 8 dimensions. And they are the exceptional cases in Berger's classification. So that is, Berger's classification has the same kind of structure as other classification problems, like the classification of Lie groups or finite simple groups. You get a number of repeating families depending upon some natural number, like U of M, SUM, SPM, so on. And then you get some small number of extra cases which just do something weird. And in the holonomy group case, these are G2 and spin 7. Just as a few kind of milestones in the theory. Well, in 1955, Berger's classification came out. Now, Berger didn't prove that the holonomy groups G2 and spin 7 actually exist, that they occur in nature, but it kind of raised them as a problem, as it were. And without Berger's classification, nobody might have thought to look. I suppose, well, if people hadn't been thinking about the classification of holonomy groups, they might eventually have thought about G2 and spin 7 in terms of manifolds with constant spinners, but that's not how things happened. Okay, so nothing really happened for 20 years, until 1987. Robert Bryant proved that there exist metrics with holonomy G2 and spin 7. Using the theory of exterior differential systems. So this is a way of analysing systems of PDEs near a point. What his proof basically showed is that you can find Taylor series of Riemannian metrics converging in a small ball around a point, which converge to a metric with holonomy G2 or spin 7. But that told you kind of nothing about the global geometry of such things, but it gave you a precise measure of kind of, in some sense, how many solutions there are. The metrics with holonomy G2 depend upon so many functions of 6 variables, that kind of thing. Okay, in 1989 rather, Bryant and Simon Salomon found explicit examples of metrics with holonomy G2 and spin 7 on non-compact 7 and 8 manifolds, including complete examples. And their method was you look at consider metrics with cohomogeneity 1. That is, you look at metrics with a large symmetry group acting so that the orbits have dimension 1 less than the whole thing, and then the condition for something to be a metric of Halomni G2 or spin 7 can be turned into an ODE upon the metrics on the orbits. And then they showed the ODE had solutions, some of which could be found explicitly. Okay, in 1993-95, I found the first compact examples. By resolving torus orbifolds T7 on gamma and T to the 8 on gamma. Okay, in 2000 I found more examples and a second construction of spin 7 manifolds, compact spin 7 manifolds, this time using Calabi-Yau 4 orbifolds. So 2001, well, so Donaldson deserves some credit too, and Alexei Kovalev, a second construction of compact G2 manifolds. So, well, the idea was due to Simon Donaldson, and I actually wrote about it in my in this book with his permission. The idea was then actually turned into a theorem by Alexei Kovalev. It was a difficult project, and he didn't do it very well in some ways. So, circa 2010, Corti, Haskins, Nordstrom, and Pacini came back to the Kovalev project and kind of did it properly. So these are kind of better references than Kovalev. But one of the things they did is that they generalized the algebraic geometry Kovalev used quite a lot, so they produced an awful lot more examples. The Kovalev construction, it starts with a suitable pair of complex threefolds, such as with some positive Ricci curvature conditions, such as Fano. So these guys showed you could use something called weak Fano instead, which led to a lot more examples. What else? Well, I suppose 2017, paper by myself and Grigianis gave a third construction of compact G2 manifolds. And that's about as far as we've got in certainly the whole constructing examples thing. So all of these examples, they come from kind of gluing together pieces which broadly come from Calabi-Yau geometry, because there are inclusions. SU2 and SU3 live inside the Halomni group G2. SU2, SU3 and SU4 live inside the Halomni group spin 7. So if you have something with Halomni SU2 or SU3, then you can take the product of that with a flat space such as a torus and get a torsion-free G2 or spin 7 structure. And then those can be used as ingredients to glue together. And I'll be explaining some of that later. Okay, so another important fact is that, okay, I told you that string theory, so supersymmetric string theory says that dimension of the universe is 10, which you split as 4 plus 6, where this is, this is space-time, and this is some small Calabi-Yau threefold. Well, there's another version of string theory called M theory. In M theory, dimension of the universe is actually 11, which you again split as 4 plus 7, where 4 is our macroscopic space-time, and 7 is some compact G2 manifold. So you want a G2 manifold because, again, you want a supersymmetry in physical language, and when you translate supersymmetry from physics into mathematics, as far as I can tell, what it means is that you want a Riemannian manifold with a constant spinor, actually the spinor which is preserved under the Levi-Cheeve connection acting on the spin bundle, and then a 7 manifold with a constant spinor has solenomy contained in G2. Okay, so you might think that therefore compact G2 manifolds should be the ingredients which M theorists want to bake their universe out of. Unfortunately, it's not quite that simple, because well, a non-singular compact G2 manifold would give you what's called chiral physics in 4 dimensions. As I understand it, chiral is a kind of reflection symmetry of some kind. So you'd be your physics should be symmetric under kind of reflection in a mirror, possibly some kind of time symmetry as well. I'm not quite sure exactly what, but actually it turns out that our observed physics is subtly non-chiral. So we want non-chiral physics, and therefore you want some compact G2 manifold with singularities. So the M theorists have some particular kind of bouquet of singularities that they want. They'd like to have compact G2 manifolds which include singularities on cones and other kinds of singularities on orbifold singularities, all interacting in some way, in order to produce some spectrum of particles doing the kind of thing they want. And at the moment we don't know how to do that. But just as in the kind of Calabi-Yau case, there's this great big interaction between string theorists and mathematicians. So also in the G2 case, well, it's rather a smaller field, but nonetheless there is a kind of important interaction between the M theorists and the mathematicians. Now, in the string theory case, the string theorists have usually been ahead of the curve, and the string theorists have been making lots of exciting predictions, which then later turn out to be true. For the G2 case, it hasn't really happened. If you ask an M theorist what the answer is to some mathematical question, they usually say, or something helpful like that. And apparently, basically, that's because there's fewer supersymmetries here, and it's difficult to make any sort of meaningful predictions for a theory with only one supersymmetry, as I understand it. Anyway, but there is this kind of interaction going on between mathematics and physics in this area. But anyway, so we don't yet know how to produce compact G2 manifolds with the kind of singularities that M theorists want, but it's entirely plausible that such things should exist. Okay, so now let's go into some details. So we'll start with, so today is going to be the Holonomy group G2, and tomorrow I'll tell you about spin 7. So we'll start with the basics. Let R7 have coordinates x1 up to x7. And as a shorthand, let's write dxijk for dxi wedge dxj wedge dxk as your standard three form in the three forms on R7. And dxijkl is dxi wedge dxj wedge dxk wedge dxl in the same way. So let's define a three form phi 0 on R7 by so phi 0 is dx 1, 2, 3 plus dx 1, 4, 5 plus dx 1, 6, 7 plus dx 2, 4, 6 minus dx 2, 5, 7 minus dx 3, 4, 7 minus dx 3, 5, 6. Okay, so let me write a couple of sentences before I say where this comes from. So the subgroup of GL7R acting on three forms on R7, preserving phi 0. So the stabilizer group of this particular three form in the 7 forms on R7, this is the exceptional Lie group G2. So a few other things about it. It is compact, it's connected, it's simply connected, and it's real 14-dimensional. And it also preserves the standard Euclidean metric G0, which is dx1 squared plus dx2 squared up to dx7 squared, and the orientation. On R7. Okay, so we're going to want to know where this three form comes from. Well, one answer would be that it comes from the multiplication table in the octonions, the Cayley numbers. So if you take the imaginary octonions to have basis E1 up to E7, then the fact that you have a dx1, 2, 3 in here comes from the fact that E1 times E2 is equal to E3, and in fact E2 times E1 is minus E3, E2 times E3 is E1, and so on. The fact that 1, 4, 5 is in here is because E1 times E4 is equal to E5 in multiplication in the octonions, and so on. So one answer is that this three form has some magic properties which come from the magic properties of the octonion multiplication, which is very special. Another answer is that this three form is not special at all. It's actually generic as a three form in R7, which I'll show you a calculation in a minute. So in that sense, it's just a particular choice of generic three form. Okay, so G2 preserves this three form, and it preserves the metric, and it preserves the orientation. So hence, G2 also preserves the four form. If you have a metric in orientation, you have a Hodge star acting on forms. And so we can apply the Hodge star to this three form, and because G2 preserves everything you use to make that Hodge star three form, it preserves phi 0 and G in the orientation. It'll preserve star phi 0, which is dx 4, 5, 6, 7 plus dx 2, 3, 6, 7 plus dx 2, 3, 4, 5 plus dx 1, 3, 5, 7 minus dx 1, 3, 4, 6 minus dx 1, 2, 5, 6 minus dx 1, 2, 4, 7. So hopefully the way I've written it, each term here is the Hodge star of the corresponding term here. So dx 4, 5, 6, 7 is the Hodge star of dx 1, 2, 3. Where star is the Hodge star of the metric G0. So on R7, the two fundamental actors in thinking about G2 structures are going to be this three form and its Hodge dual four form. Okay, and well, since G2 preserves G0 and the orientation, it's a subgroup of the group which preserves these two. So G2 is a subgroup of SO7, but that's got dimension 14, that's got dimension 21, I think. So it's a proper inclusion. So let's suppose that X and G is a Riemannian submanifold with the Lonely group of G could be equal to G2, but actually being contained in G2 is enough. So then, by the correspondence between holonomy groups and constant tensors, then there is a natural three form phi and a Hodge dual four form star phi on X. And they're constant tensors, so they have nabla phi is nabla of star phi is 0, where nabla is a Leverage connection of G, and it's worth noting that these imply that d of phi is d of star phi is 0, as the d of these things is just a component of the derivatives as nabla is torsion free. And such that at each point little x in big X, there are isomorphisms t at x to big X gets identified with R7. So the isomorphism is not unique, but it's unique up to the action of G2 on R7, and these isomorphisms identify G0 and phi 0, well, now let's say G at x, phi at x, and star phi, sorry, phi at x with G0, phi 0, and star phi 0. Okay, so this is just a fact from the way Halomny groups and things preserved by Halomny groups correspond to constant tensors. Okay, so when we're thinking about metrics with Halomny G2 or Halomny contained in G2, it's much easier to think in terms of this 3-form phi and its Hodge star 4-form star phi than to try and work just with the metric or to work with the G2 structure in the sense of some principal subbundle of the frame bundle. So basically you get used to thinking about G2 structures in terms of these special 3 forms. Okay, so let's make a definition, which is really an abusive notation. So we're going to say a G2 structure, brackets phi comma G on X, let's say on an oriented 7-manifold big X, is a 3-form phi and a Riemannian metric G, on X, such that at each point little x in big X, this happens. There are isomorphisms t little x to big X gets identified with R7, which identify these guys, G at x, phi at x, star phi at x, with G0. Actually, well, we don't need the star phi, it'll be automatic. So which identify G at x and phi of x with G0 and phi 0. Okay, so that's our notion of G2 structure. We're not requiring nabla phi as nabla star phi is 0 at this point. We just require the pointwise conditions, not the partial differential equations. Okay, so this is an abusive notation because we already have a definition of G2 structure, but this is equivalent to the standard definition of G2 structure, as a principal subbundle P in F of the frame bundle. Okay, so I've already given you a definition of G2 structure. It's a rather abstract thing, not very easy to work with. It's a principal subbundle P in F, where that has structure group GL7R, that has structure group G2. There's a natural one-to-one correspondence between those things and these things, so I'm going to call these G2 structures. And actually, phi determines G in a G2 structure, because the stabilizer group of phi is G2, but it's convenient to have phi and G there together just in your notation. So I like to write them as pairs like this. Well, let's come back to the question of what's special about this free-form phi 0. The orbit of phi 0 under GL7R is actually isomorphic to GL7R divided by G2, because G2 is the stabilizer group of phi 0, which has dimension, the dimension of GL7R, which is 7 squared, 49, minus the dimension of G2, which is 14, is 35. But the dimension of the three forms, lambda 3 R7 star, this is the binomial coefficient 7 choose 3. So 765 over 321, which is also 35. So the orbit, this is a kind of submanifold of that, which has the same dimension, so it's actually open. So hence the G2, the orbit with GL7R, orbit of phi 0 is open in lambda 3 of R7 star, and the G2 form phi 0 is generic. So in that sense there is nothing particularly special about it. So in fact, if you look at the orbits of GL7R on all of the three forms, there are two open orbits. One of them is the orbit of phi 0. A second one has stabilized the group a non-compact form of G2, called G2 star sometimes. So that would be a kind of version of G2 which is compatible with a metric of mixed signature, signature 3, 4. So that will be going off in the direction of kind of Lorentzian or indefinite geometry, which we don't want to do. And then there are a bunch of other orbits of smaller codimension, such as the orbit of 0. Okay, so now this is actually a useful thing for us, because if you want to deform your G2 structure a little bit, you can just deform the 3 form a little bit. So if you have a G2 structure with the 3 form phi, you add any small 3 form, C0 small 3 form onto it, you'll get a different G2 structure with that 3 form. So that is a very useful tool when thinking about deforming G2 structures for various reasons. Okay, so let's state a proposition. Let's call it proposition 5.1. So if we let big X be a 7-manifold and brackets phi comma g a G2 structure on X. So then the following are equivalent. So firstly, d of phi is d of star of phi is 0. Secondly, well, maybe we would like to write the star as star phi, because star is a Hodge star of G, and G depends upon phi. So you can think about this Hodge star operation as depending upon phi. Secondly, nabla of phi is nabla of star phi of phi is 0. And thirdly, the holonomy group of G is a subgroup of G2. That's not quite enough because you want phi to be attached to G in a super way. So we say, and phi is the associated free-form. That is, if you have an inclusion, a particular inclusion of the holonomy group of G in G2, then from that you can reconstruct the free-form phi by some kind of parallel transport argument. Okay, so this is a bit like the theorem about Kähler manifolds, which says that d omega equals 0 is kind of equivalent to nabla of omega equals 0, even though these equations are apparently much stronger than those equations. It can be true because phi and star phi, well, as a pair, these are not kind of generic. This is determined pointwise by that. Okay, so when these happen, so then we call phi comma g a torsion-free G2 structure. So that's equivalent to the kind of previous notion of torsion-free G2 structure in the language of G2 structures. And I'm also going to call the triple X, phi, and G a G2 manifold. So for me, a G2 manifold is a manifold with a torsion-free G2 structure. That's not a universal notation. Some people you would use G2 manifold just to mean a manifold with a G2 structure, and then they talk about torsion-free G2 manifolds. But I find it irritating to keep saying torsion-free all the time. And you should note that although d phi is d of star phi is 0, or maybe star little phi is 0, these look like linear equations on our data phi. Actually, this operator star phi depends on G, which depends on phi. So actually, d of brackets star phi phi is 0 is really a non-linear equation on phi. So we're really in the business of solving, well, if we want to study torsion-free G2 structures, we have to solve these non-linear PDEs. Okay, so Well, so a G2 manifold, brackets X, phi, G, has topological invariance so you've got a closed free form. You can form its de Rham cohomology class brackets phi in the third de Rham cohomology of X, and you can form the de Rham cohomology class of star phi in the fourth de Rham cohomology of X, which are similar to the Kähler class of the Kähler metric, and if phi and G is torsion free, so the holonomy group of G is contained in G2, then G is Ricci flat. Okay, so some more important stuff. We can think about holonomy subgroups of G2. Well, so we have, think about SU2. If we let SU2 act on R7 by splitting R7 as the direct sum of R3 and C2, where on here we put the trivial action, the trivial SU2 action, and on here we put the standard SU2 action. So under these conditions, SU2 is actually contained in G2, contained in SO7. And so, if you have some four manifold Y, H with the holonomy group of G, of H is SU2, so you have some Calabi-Yau twofold, then, well, basically R3 cross Y and some G flat metric on R3 cross H, and also let's say T3 cross Y and again a flat metric on T3 cross H. These have well, holonomy contained in G2, so they're torsion-free G2 structures. So if you have a Calabi-Yau twofold, something with holonomy SU2, in 4 dimensions you can take the product with a flat thing like R3 or T3 and then get a torsion-free G2 thing. That will be important later as a kind of to make ingredients out of which to build things which have the full holonomy G2. And similarly, if you have SU3 acts on R7, which is R direct sum C3 with the trivial action and the standard action of SU3 on C3, then SU3 is contained in G2. So if you have a 6 manifold Y with a metric H with the holonomy group of H is SU3, then well, R cross Y and also the circle S1 cross Y have torsion-free G2 structures. Okay. Right. I'm not going as fast as I wanted, so I think I'd like to run over by a couple of minutes, if that's all right. So next I want to give you some facts about compact 7 manifolds with holonomy G2. So the first of all, let's give you a proposition, 5.2. So let's suppose that x and phi and g is a compact G2 manifold that means that this is a torsion-free G2 structure, so the holonomy group of G is a subgroup of G2. We'd like to know when is the holonomy group strictly equal to G2. So that the holonomy group of G is a subgroup of G2. So then the answer is the holonomy group of G is actually equal to G2 if and only if the fundamental group of X, phi1 of X, is finite. So X can be simply connected or have finite fundamental group. And then the proof involves some facts about Ricci-flat metrics, the Cheeger-Gromov theorem, and then some other facts about holonomy groups. Okay, perhaps I'll stop there for now.